Right, so welcome everybody. So this is a Flow seminar where Flow seminar stands for Federated Learning One Word Seminar, and Flow was created to provide a global online forum for the dissemination of latest scientific research results in all aspects of federated learning, including but not limited to distributed optimization, learning algorithms, privacy, cryptography, personalization techniques, communication compression systems, hardware, and also new generation of models. So today it's already our 93rd talk, and it's my great pleasure to introduce you our speaker for today, Firooz Shahriari-Mehr, who is a PhD student in the Department of Computer Science and Engineering at Chalmers University of Technology. And in his research, he mainly focuses on the large-scale machine learning and optimization. And today, he'll tell us a bit more about decentralized constraint optimization. So thank you, Firooz, for agreeing to give a talk. It's a great pleasure to have you here. And please, stage is yours.
Yeah, thank you, Samuel, for introducing me and being our host today. And after that, I would like to say hello to all the participants. Thank you for coming. It's my great pleasure that today I'm going to introduce my research to you, which is about decentralized constant optimization and our new proposed algorithm called double averaging and gradient projection. This talk has three parts. As first, I will introduce the decentralized constant optimization problem, and I will say why we are interested in this setup. And after that, in part two, I will introduce the AGP algorithm for this specific setup. I will talk about the building blocks of our algorithm. And after that, I will show some experiments to show the efficiency of the AGP algorithm. And in the last part of the talk, I will introduce the new methodology called aggregate lower bounding, which can be used to prove the rate of convergence for general optimization methods. And using this methodology, I will prove the rate of convergence for gradient descent when the objective function is smooth. And after that, I will prove the rate of convergence for the AGP. Introduction part, why we are interested in decentralized constant optimization. At first, why decentralized setup? Nowadays, the data is distributed on edge devices, and due to privacy concerns or communication or memory limitations, we cannot send the data to one node to process the data. For example, in the application that we have several hospitals which are connected to each other, and the goal is to solve a supervised learning task to find a classifier to predict whether new patient has a specific disease like COVID or no. We have to solve an empirical risk minimization, but here the data of patients is private and we cannot send it to one big cluster to find the model parameters. So the goal is to find the model parameters in a distributed way without sharing the data by using the empirical risk minimization. This problem can be written in this finite sum minimization form, where f(v) of x shows the local objective function of each node, which is the empirical risk at that node related to the data points at each agent or each hospital in this example. And to solve this finite sum minimization or decentralized optimization, the nodes can communicate with each other. Based on the communication network among the agents, we can have two setups in distributed optimization. The first one is centralized setup when there is a master node which orchestrates all the workers, but when the size of the problem is very large, for example, when the number of nodes increase or when the local solution dimension is large, we might have master failure problem or master bottleneck problem. This is the reason that we prefer decentralized setup. In decentralized setup, we don't have any master node. So at the end of the optimization, we should be able to read the solution from any node that we want. So we hope to reach to a consensus solution, which means that the nodes should agree on one solution. And in the literature for decentralized optimization, there are too many papers. And if I want to categorize them, first of all, I can categorize them based on whether they have considered constraints or no. The the first setup when we don't have any constraints is called decentralized on-constraint optimization, and the second category when we have constraints, we can have two scenarios. One of them is where the constraints are distributed among the nodes. This is what we have in this paper. You can see each node besides local objective function has its own local constraint set, F1 and S1. And in the literature, there are some papers that they assume that the constraints are identical among the agents. So they have common constraints. The second way to categorize the optimization algorithms in this setup is based on the communication network between the agents. Depending on the environment, we can have bidirectional or unidirectional communication links. And in this figure, the communication links are represented by the edges of the graph, where the edges are simple, they are not directed. It means that the nodes can both send and receive from the other one. But when we have directed edges, it shows that only node 1 can send to node 2, which is called a directed graph, to show the communication links are unidirectional. Based on these two characteristics, we can do a kind of literature review. Then we don't have any constraints. I don't want to talk about the papers in this setup. There exists a great literature, but in the next two slides, I will make it clear why we are interested in constraint setup and why we should consider constraints explicitly. Then for the setup when we have constraints, we can categorize the papers based on undirected graphs and directed graphs. When the graph is undirected, there are some papers that consider distributed constraints, but when they want to prove the rate of convergence, they assume that the graph is fully connected or the constraints are identical. So the convergence proof is not general for those papers. And when the graph is directed, there exists an algorithm called DDPS. This paper assumes that the constraints are identical, and for the convergence to the optimal solution, it needs a diminishing step size. And we know that using diminishing step size, we decrease the rate of convergence. So the place of our paper in the field is where we have constraints, the graph is directed, and the constraints are distributed. And our paper is the first one that uses fixed step size to converge to the optimal solution in this setup. Now I want to say why we are interested in constraints. If I told you that there is a great literature for unconstrained optimization, and if you ask the authors of those papers what you will do when you have constraint, they will say that we will add the indicator function of the constraints to the local objective function, and then we will use the methods that exist for the unconstrained optimization. But the problem here is that they neglect the assumption that they have for convergence proof, which is the smoothness of the objective function, because the indicator function is not smooth. And if they say, okay, why should we care about constraints? I can say that there are some applications that are naturally constrained, for example, optimal transport or SVM. Moreover, in the paper, we show that any unconstant optimization with a non-smooth objective function can be reformulated as a constant optimization. So this is the second reason that constraints are important. And in this slide, I will show how we can reformulate any unconstant optimization with non-smooth objective function into a decentralized constant optimization where the objective function is smooth and the constraints are epigraph. If we consider this problem and assume that the number of nodes is equal to 1, so we are going to minimize the function f here, and we can see that the minimum is here at x star. Instead of minimizing this problem, we are going to minimize x and t, where t is the sublevel set as here. We will minimize t until there exists a point in the epigraph of the function. So this is the epigraph formulation of the problem. And these two problems are equivalent. Yeah. In the paper, if you look here, you can see the reformulate problem. The constants are epigraph of function fv. And the only oracle that we can compute in optimization methods when we have constant is projection onto the constant set. So to be able to introduce optimization methods, we need to compute the projection onto the epigraph of function. And in the paper, we have proposed a new method based on proximal backtracking to project onto the epigraph of a function. And the reason for introducing a new method was that the previous methods were restricted to solving complex equations or computing the proximal of more complex function than f. In this method, by writing the definition of the projection, which is here, minimizing this, subject to x prime and t prime, they are in the epigraph, writing the Lagrangian formulation of this minimization, we can see that the x dagger and t dagger are equal to proximal of tau f at x and t plus tau, where tau is the solution to this maximization problem. This problem is strongly concave, and we can use any first order or second order method to find the solution of tau. But here we are interested in backtracking to find the solution faster. So what we do is that we have point x and t, and we want to compute its projection. So first we will check whether we are in the epigraph. If we are in the epigraph of function f, then it's done. If we are not in the epigraph of f, then we will pick a step size theta. We will initialize tau by a positive value. Then for that, then we will compute proximal of tau f at x and t plus tau, and check whether we are in the epigraph or no. If we are in the epigraph, then it's done. Otherwise, we will use gradient ascent to update tau, and again compute these two terms and check the condition whether we are in the epigraph or no. And in this way, we can project to the epigraph very fast. So this was the first part. To summarize, I introduced the decentralized setup. We have distributed constant directed graphs, and we are going to solve this decentralized constant optimization over this decentralized setup. Any questions until here?
So just one clarification question. So here in your decentralized setup, you assume that each node has only access to the subset of constraints, right? Doesn't need to access
Yes.
all the constraints. Okay.
Yeah.
Thank you.
Okay, I can continue to the second part. In this part, I want to introduce the DAGP algorithm for this setup, and then show some experiments for it. The DAGP algorithm, I agree that this slide is a bit confusing. Don't look at the iteration here. I just want to show you that the algorithm is based on several blocks. Here we have 4 blocks, where in the following slides, I will introduce these blocks one by one, and each of them is based on its previous block. And at the end, again, I will come back to this slide, and I hope we understand the DAGP algorithm, and we have some sense about how it works. The first block is weighted averaging. We have 2 weighted averaging in the DAGP algorithm, one of them here using gossip matrix W, and the other one here with gossip matrix Q. Since each node has only its own local objective function and its own constraint set, the oracles that each node can compute is the gradient of FV and projection onto its constraint set. In the second block, I will show you that if we only use these two oracles, it will not converge to the optimal solution, and we need to add a tracking term called G and track the gradient of visible directions. And at the end, to reach to the optimal solution, we need to use the distributed null projection concept. Now let's see these blocks one by one. The first block is weighted averaging. Assume that the nodes don't have any objective function or constraint. Each node has its own initialization value, x v of 0, and the goal of the network is to find the consensus average solution. So what each node can do is to send its local solution to its out neighbor, and after that compute the weighted average of the received information. For example, here node V is receiving from node 1 and node 2, and we will assign a weight for the received information from node 1 by WV1. And then these communications can be represented by a gossip iteration, where we can see that the next value of the next value at iteration k plus 1 for node V is equal to the weighted average of its current solution and the received information from neighbors U in the neighborhood of node V, the input neighbors. Then if we put all the gossip weights into a matrix called gossip matrix and put all the local solutions as the rows of matrix X, then the gossip iteration can be written as xk plus 1 equal to I minus w xk by recursion I minus w to the power of k x0. Here, to reach our goal, which is to reach to a consensus average solution, and we have the power to build this W matrix, we have to design W in a way to reach our goal. And the characteristic that this gossip matrix should have to reach to a consensus average solution is that it should satisfy both zero row sum structure and zero column sum structure. For undirected graphs, then the communication network is bidirectional. Easily using the Laplacian matrix, we can create this gossip matrix and we can reach to a consensus solution. But when we have directed graphs, we can either have zero row sum structure or zero column sum structure. When we have zero row sum structure, where the gossip matrix is represented by W, we can see that the solution, the final solution of each node is a consensus solution, but it's a weighted average of the initial values. And when we have zero column sum structure, the solution of node V will be pi of V multiplied by the average of initial values. And in the literature, people will use push-sum method or push-pull strategies to deal with this. For example, here, write eigenvalue by estimating it and then solving the problem. So this was the first block, weighted averaging, which represent the communication among the agents. The nodes communicate with it themselves to find the solution. The next block is objective minimization plus projection. Now we bring the objective functions and constraints back, and we want to solve this problem. The optimal condition for this problem is that x star should be x star is the solution of this problem if it satisfied this optimality condition, where the round of ISV at x star is the normal cone of constraint set SV at point x star. And here, for example, if you have two sets, convex sets S1 and S2, and this point is their intersection, the normal cone to S1 is round of IS1, and the normal cone to S2 is round of IS2. And then for the intersection of S1 and S2, we have this cone, and all elements and all vectors in this cone are the elements of the normal cone. Okay, so we want to solve this problem, and the solution should satisfy this optimality condition. From the previous block, we know to reach consensus, the nodes should do a weighted averaging, and the only oracles that they can compute is the gradient of f, and after that projection onto their constraint set. So if we align the solution of the weighted averaging by minus a step size mu multiplied by gradient of f, and since we might come outside the set, for example, at node 1 here, you can see the z variable can be outside the set S. So we will project onto the constraint set, and we are in the constraint set from the second iteration. Here, I also wanted you to see that z minus x is an element of the normal cone, and it's negative. This direction is a direction to the constraint set, where in the talk I will say the name the physical direction, and by that I mean this vector minus this vector. Okay, this is the distributed projected subgradient algorithm, where we only use the gradient on projection. And in the optimization theory, we have the analysis of fixed points, where we see if the algorithm converge, at what point it will stop. So if we write the analysis of fixed point for this algorithm, we will see it will stop at the point that 0 is an element of partial of ISVX star plus gradient of FV. This is only one term of this global optimality condition. The global optimality condition is the summation of all these terms. But here we only have one of them, which means that each node will minimize its own local optimization problem, minimizing FV such that X is in the constraint set SV. So we will have a variance for this. We will have a distributed variance for this method. And to converge to the solution, since this point might not exist, they have to use a diminishing step size to reach to the optimal solution. So here you can see that since we are minimizing each node is minimizing its own objective function subject to its constraint, I will say that this is a greedy alignment and this is a greedy projection. And we have to modify these greedy alignments to reach to the optimal solution. This is the reason that we have to introduce a new variable to track the average of gradients and feasible directions to average this global optimality condition. For this, similar to the variance reduction techniques for stochastic optimization, here we introduce a new variable called G to track this average. And the update true for G is here in equation 1, when it will be updated as the complex combination of its previous value plus the new information about the gradient of f and a normal vector to the constraint set, a feasible direction. Then we have to design a dynamical system to track the average of gradients on a feasible direction. To track the G will be updated in this way, and for this dynamical system, we can assume that the input is this term, which is one element of the global optimality condition. To reach to the optimal solution, we have to satisfy two desires. First of all, make GB variables equal to DV, and then design the algorithm or design the dynamics in a way that summation of G is equal to 0. And this is called null condition. And to satisfy this second desire, we have a concept called distributed null projection. In this concept, we introduce extra variables HP, which act as the distributed projection of GB variables. For this HP variables are in a space where the null condition is always satisfied. The space that summation of HP is always equal to 0. And to create this space, first we consider that the Gossip matrix Q has 0 columns on a structure, and we initialize HV variables by HV 0 equal to 0 by 0 vectors, and we will update H using this equation. Since Q is has 0 column sum structure, the summation of HV over all iterations is equal to 0. So we have this space. And the last thing that we should do is to make G variables equal to H variables to satisfy. If G become equal to H, then summation of G will be also equal to 0. And for this, we will add the feedback term H minus G to the update rule of variable G. Here, we will add the feedback term to make G equal to H. And from the last equation, we know that the summation of H will be equal to 0, and then we will have optimality. So again, we are in the DAGP algorithm overview. Now we know about the blocks, weighted averaging, objective minimization, projection. We understand why we need this G variable, because we have a distributed variance, and we will use a variance reduction technique. And to satisfy the optimality condition, we will have this distributed null projection concept. And this was the algorithm. If you have any question related to the algorithm, I can answer.
Yeah. So here, just one clarification question. So in your construction, are any components here like kind of interact with each other, or you can kind of like when you do the analysis, can you kind of almost isolate, analyze them in isolation?
Analyze different blocks, you mean?
Yes. So how much they actually kind of like interact, like this kind of changes. So are they kind of like orthogonal in a sense, or they are also like dependent on each other?
No, they are completely dependent on each other, especially the last two equations. Okay. This distributed null projection is and this gradient and physical direction tracking, they are combined to each other. And this feedback term, when I was talking about it, I said that it's for satisfy the optimality condition. But we also need this HV variable here, because if you look at the update rule of GV, you see that we only add the information about the gradient of F and the feasible direction at node V. But the node should communicate this information with the neighbors, and this will happen using this H variable. This is the second reason that we have to introduce H. And meanwhile, when we gossip this information, we have to keep the summation of H equal to 0 to satisfy the optimality. So the analysis of them is completed together.
Understood. Yeah, thank you.
You're welcome. So if there is not any question, I can move forward to experiments. Here I have some general details about the experiments. Random strongly connected directed graphs are used as communication networks. W and Q are computed using the Laplacian matrices. For the methods that need row stochastic or column stochastic matrices, I use I minus W and I minus Q. And finally, feasibility gap and objective values are computed at X bar, which is the average over all, average solution over all nodes. I have 3 experiments. The first experiment is decentralized constant optimization, where the objective functions and constants are synthetic. In the second experiment, I have the problem of logistic regression for 2 digits of MNIST. That one is unconstrained problem, and I only want to show that our DAGP algorithm can also be applied to the unconstrained setup. Here we don't have any projection, and X is equal to Z, so we can use it for decentralized unconstrained optimization as well. And the last experiment is optimal transport, which is a practical application, and we just want to show the efficiency of DAGP. So in the first experiment, the synthetic functions are log of cosine hyperbolic of linear functions, and the constraints are some half spaces. We have 2 setups. In the first setup, I assume that we have 10 objective function or 10 nodes, and the size of the problem is 20. So the feasible set is large. And probably the solution of the unconstrained problem might be in the feasible set. So the constraint might not be active, and this is what we see in this picture. For DHGP, we are in the constraint set very fast, but for DDPS, we are going to the constraint set very slowly. And here we have the objective value, which for DHGP, we have a linear rate of convergence, but for DDPS, it's sublinear. Also, I want to show you that I plotted the difference between the solutions of two different nodes for several nodes. We can see that the nodes reach consensus. And also I plotted the norm of summation of G, which we can see the summation of G is also going to 0, which says that the optimal, the stopping point is the optimal solution. In the second setup, I assume that I have 20 nodes and the dimension is 10. So the feasible set is smaller and some constraints might be active. So again, for DHGP, we are in the constraint set. We go to the feasibility gap is equal to 0. But for DDPS, we are only close to the feasible set. And this is the reason that we achieve a smaller value for DDPS here. But we can see that we converge very fast for DHGP. The second experiment is logistic regression for 2 digits of MNITs. This is the MNITs data set, and this is the logistic regression loss. It is strongly convex, which is needed for push-pull and adopt algorithm. And if we run DHGP and these two, we can see that DHGP performs similar to push-pull, and it performs better than adopt algorithm. And push-pull is the state of the art for decentralized unconstrained optimization. So our algorithm not only handles constraint, it can also be used for decentralized constraint optimization. The last experiment is optimal transport problem, where we have two distributions. We want to transport a mass from source to target, from source distribution to target distribution. How much mass should be transported is in the transport plan matrix called X, and the cost of the transportation is in matrix C. Matrix C shows the cost of the transportation, and this is a linear program, and we can, in the paper we show that we can write it in a decentralized framework of our paper in this way. The constraints are simplices, which we can project onto them simply, and also the objective function is linear. Here NS and NT are the number of source and target points. In the next experiment, I assume both of them equal to n, and also I should say that C and X are of size NS by NT. So when NS is equal to NT equal to n, by increasing n, the size of the problem increases, and if we use a linear program solver to solve this linear program, we can see that the running time increases very fast. But for DHGP, it's possible to find the optimal solution in an appropriate time. Yeah. And in the next slide, I have optimal transport for domain adaptation. In this practical application, I have a source distribution and target distribution. For source, I know the labels, so I can find a classifier, but I want to use this classifier for the target domain as well. I will assume that the shift in the data comes from a map, and I will compute this map using a optimal transport problem. Then we can find a classifier which can be used for both source and target distribution, target data sets. In this problem, the size of the problem is the size of cost matrix and transport plan is the number of data points at source data set multiplied by the number of data points at target data set. For if the data set that we consider is MNIST and USPS, then those matrices are of size, for example, 60,000 by 12,000. And from the previous experiment, we know that linear programming solvers cannot find this solution. In the literature, people will introduce the regularized version of the optimal transport and use synchrone algorithm to solve this problem. But by introducing the regularization, the solution will not be sparse anymore. And in this problem, we are interested in a sparse solution. So we are interested to find the solution of this problem, not the regularized version. And this can be achieved using the DAGP algorithm in a decentralized way. We can see that the transport plan is sparse here, but for when we use synchrone algorithm is more dense than DAGP. Yeah, this was our experiments. Any questions related to them?
Yeah, I don't see any questions, so I guess you can continue.
Yeah, perfect. Okay, the last part of the talk, the convergence analysis of the AGP. In this part, I want to introduce a new methodology called aggregate lower bounding, which can be used for different optimization methods. At first, I will start by introducing the classical proof for gradient descent based on Lyapunov functions. I will talk about the idea behind it and how we can use this idea to introduce this methodology. And after that, I will provide the rate of convergence for both gradient descent and the AGP algorithm. To start with analysis of gradient descent, when the objective function is smooth, we have gradient descent dynamics. And also from convexity, we have these two relations. Also, we can write a smoothness inequality by writing it at points xk plus 1 and xk. Then by doing some basic calculations, for example, subtracting f star from both sides, then using this inequality, applying the dynamics of gradient descent to the resulted inequality, we will have this gray inequality here. And in the classical proof, people will use algebraic inequalities to write this inner product as the difference between this Lyapunov function at xk plus 1 and xk. And then they will say if mu is less than 1 over L, and summing over all iterations from 0 to k minus 1, and using Jensen equality, we will have order of 1 over k rate of convergence. If we look at this proof to see what the idea is, here, this is the gray inequality. We can see that the first part is a positive definite function, which is always positive, and it will be equal to 0 only at the optimal solution. And we show this by phi of psi k, where psi k shows the state vectors of the optimization method. For example, for GD, it's only xk and xk plus 1. And the next two terms, I will show them by ak. And in the classical proof, we have to find some Lyapunov function and lower bound ak by the difference of this Lyapunov function at 2 successive iterations. Then we will add all the ak's together, which is represented by a bar of k, and it's called aggregate term. Then we can show that this aggregate term is lower bounded by minus L of psi 0. And finally, the summation of phi of psi k is less than L of psi 0, multiplying by 1 over k, and using Jensen equality, we will have order of 1 over k rate of convergence. But the complexity of this classical proof is finding these Lyapunov functions, especially when the algorithm is very complex. Finding these Lyapunov functions become more complicated. In the new methodology that we have, we don't want to find these Lyapunov functions anymore. Instead, we are going to find the minimum value of the aggregate term, a bar of k, in an abstract optimization over all possible trajectories of the parameter psi k generated by the dynamics of the algorithm. In this methodology, we have to write the dynamics of the algorithm in this way: psi k plus 1 equal to r psi k plus px of xk plus 2. And also we can write the aggregate term in a matrix form with a matrix called S. Yeah, in this quadratic form. We will assume that the lower bound for a bar of k is minus c norm of psi 0. And to show this, we can have this optimization problem. And we have to show 0 is the solution of this optimization. If 0 is the solution of this optimization, this term, which is a bar of k, is lower bounded by c norm of psi 0. And the constraint of this optimization is the dynamics of the algorithm. Yeah, to show 0 is the solution of this minimization, we have several lemmas in the paper which prove that, and for that we need one assumption to be held, which is a required assumption that the roots of the determinant, the roots of the determinant of f beta of z, this matrix, should be simple and real for all positive beta. So just to make the methodology clear, if we have this required condition, the roots of f beta of z are simple and real, then 0 is the minimum of this optimization problem, and then a bar of k is lower bounded by minus c norm of psi 0. And if we show this, we can have the order of 1 over k rate of convergence. Now let's see the proof of gradient descent convergence rate using aggregate lower bounding methodology. We have the aggregate term from the Gray equation. To translate it into our methodology, we will define the state vector psi k x bar of k plus 1 and x bar of k. We can write the dynamics of the algorithm in this way with these R and P matrices. Also, we can write the aggregate term in this form with this matrix S. If we compute the determinant of f beta of z, we will have this polynomial degree 2 polynomial equation, for which we can show if mu is less than 1 over L, the roots are always simple and real. So we have order of 1 over k rate of convergence with mu less than 1 over L. Now we want to use aggregate lower bounding methodology similar to gradient descent to prove the rate of convergence for DAGP. This time we also have projection. The first part is combining relations from convexity, smoothness, and projection. We will also plug algorithm dynamics into the existing relation. It's kind of complex. For details, you can see the papers. But at the end, if you combine all these inequalities, we will have this relation. The first part is the phi term, which has several terms. Each of them show required for the convergence, for this one for consensus and this one for optimality and feasibility gap. And the other terms are called the aggregate term, a bar of k. So if we show that the required condition is satisfied, first we have to translate these equations into the aggregate lower bounding methodology. We will define psi k with these state vectors. R and P will be in this form. I agree this is a bit complex, but here I just want to show you that we can write it into the aggregate lower bounding methodology. And if the required condition is satisfied, then we can lower bound the aggregate term, and we are done with the convergence rate. Since these matrices are complex, we cannot compute the determinants easily. So we use a MATLAB script to show that there are some hyperparameters. There exist some hyperparameters. First, we fix rho, alpha, and eta parameters. Then for all beta and mu in this grid, we will check whether the roots are simple and real. And here we have the feasible area. We can see that if the step size is less than this point, for all positive beta, the roots are simple and real. So there exists a combination of the hyperparameters. And after that, we fix mu, and for different alpha and rho, check feasible parameters. And we can see that there are too many combinations that we can use to that for those parameters, the required condition is satisfied. And we can lower bound the aggregate term. And at the end, by that lower bound, we can reach to the convergent rates for DAGP. Here, the first rates for the consensus, we can see the solutions of each node will converge to the x bar of k with rate of 1 over k, and the feasibility gap decreases with order of 1 over k as well. And the optimality gap is lower bounded by two terms, one of them order of 1 over k, the other one order of 1 over square root of k. So the rate of convergence for the optimality gap is finally 1 over a square root of k. And here the constants have some meanings. C0 is norm of size 0, which is the distance between the initial point and the optimal point. C should be larger than minus the minimum eigenvalue of matrix S, which kind of matrix S is also dependent on gossip matrices. So it's dependent on the characteristics of the graph. And C2 is the variance of the distributed variance, which is decreases here in our algorithm. So that was the rate of convergence. And now I can conclude the talk. We reviewed the decentralized constant optimization. I presented the DAGP algorithm and shows its effectiveness through extensive experiments. And at the end, I introduced the aggregate lower bounding methodology to prove the rate of convergence for general optimization method. And I showed you the proof of GD and DAGP using this methodology. Thank you, anyone. Thank you very much for your attention. And if you have any questions, I'm here to answer.
Thank you for a very interesting talk, Firooz. Yes, if you have a question, just as a quick reminder, please either raise your hand or just post your question to the chat, and then I'll try to unmute you. Yes, maybe just a quick one. So for the setup that you consider, are there any known lower bounds? Because you showed the upper bound for your algorithm. Are there any known lower bounds?
Lower bounds. Lower bounds for what? Sorry.
So for the setup that you considered, so you did this decentralized optimization, decentralized setup with different constraints per client, and with exactly with your Oracle. Yeah.
I understand. I don't know. I haven't seen any paper. There are not too many papers that consider these distributed constraints.
Yeah.
There is only one paper that I saw, and for that one, the convergence is limited, and also it doesn't converge to the optimal solution. I showed you it will converge to a neighborhood of the solution. So I think this is a good direction that we can work on and consider constraints. Yeah. And
maybe like other thing, do you actually think that in your setup, so with like distributed optimization with this particular constraint, like can you maybe like accelerate your method, or you think it wouldn't be possible?
Acceleration.
Yeah.
I'm not sure, you know, the rate of convergence is order of 1 over square root of k for optimality gap. I agree. But I think it's one, you know, we have the gradient tracking, so we are using fixed step size.
Mhm.
And we are also using two gossip master, which is similar to the push-pull algorithm for decentralized on-constraint optimization, which gives the fastest rate of convergence.
Mhm.
I don't know, we can use other acceleration methods to reach 1/k, or no.
Firooz, may I also add some of my own thoughts?
Yeah, definitely.
Yeah, so I mean, as you see, the algorithm is kind of inspired by variance reduction techniques in general, and in particular Saga. That means that a kind of an acceleration is already embedded in the algorithm, and 1/√k, I think, is generally believed to be a lower bound for this as well. So all in all, I'm not sure that you can accelerate it more. You can consider more sophisticated machinery, but again, we haven't looked at it very carefully. But again, it might be more difficult to consider.
Okay, yeah, understand. Yeah, hey, thank you a lot.